Alright, in this video, I want to talk about impedance loading on an amplifier. That's something that was never covered in, any of the textbooks I ever read, at least going up through basic semiconductors. So, here you see the normal case that's covered in a textbook, which is a resistive load. Alright, and here's the power across that resistor, and you can see it peaks at 194 watts here. It's an 8 ohm load, and you can also see the power of the transistor here. You can see it peaks at 80 watts, dips down here to 56 watts, and goes back up to 80 watts. And if Falstad doesn't allow you to calculate actual average power, but you can kind of look at it and see over a full wave, well, it'd probably be somewhere around 28 watts or something like that, just by eyeballing it. As far as the transistor's average power dissipation. But at any rate, the reason I'm doing this has nothing to do with just playing around with Falstad. It's about a series of articles I was kind of reading that made me curious, and this is from the Elliot Sound Products. They have a lot of really in-depth articles. It's all about sound, but boy, I'll tell you, you can really learn a lot of interesting things here. About electronics. Let's see. I think I'm on the wrong page. Yeah, this is it. So this is all the frickin' articles on electronics, and a lot of this stuff, I'm not so much interested in sound, but there's a lot of applicable stuff to sound, and these articles are just so in depth. It's like I said, I've been trying to read through as many of them as I can. But one of the articles in particular was the one I just had up. Not sure where it is. Let's see. Piece of shit. I hate Windows. Hate Chrome too. Let's see. Yeah, it's right here. It's phase angle versus transistor dissipation. Honestly, if you just Google that, you're probably in a better boat. I may try to put a link to this thing if I remember in the description of the video. But it basically is an article kind of talking, somewhat briefly, but kind of talking about what happens in an amplifier when you load it with inductive loads. That's kind of the subtext here. That's what interested me, is that part of it. The whole article is not really about that, but it does actually cover this in a way I've never seen covered before, because I've never seen any textbook talk about what actually happens when you have a reactive load. And it covers in here things like the power factor and everything, but it basically talks about, well, let me make sure I'm on the right thing here. Hold on. Yeah, this is the right article. I zoomed it in so it's easier for you to kind of read here, and made the drawings bigger, so but yeah, one of the little passages in this paragraphs here that caught my attention was talking about the worst case never achieved with any loudspeaker is a 90-degree phase shift. The cosine is 0, power factor 0. This means that the voltage across the transistors at minimum turn fully on. When it's at minimum, the current is also at minimum. This seems pretty good, 0 dissipation. Okay, the problem is that the converse is so, so when the voltage across the transistor is at maximum, so is the current. Okay, that's not really true, as it turns out. I had a hard time reconciling, okay, how is it that if a transistor is fully off, because that's when you're going to get maximum voltage across it, how is it have current going through it. And worse yet, they're talking about an inductive load here. So I'm like, well, if it's an inductive load, that means it's reversed its polarity, and it's trying to get rid of current. It's trying to maintain the current. Well, it's not going to be able to force current through a transistor in that way. I was really kind of confused, as to how it could try to force a transistor to maintain current, in that level. So there must be something more going on here. And he wasn't really that specific on what kind of amplifier he was talking about, but I assume it's for any amplifier. But, it certainly occurred to me, and especially since I'm kind of curious about using a stereo amplifier as a general purpose lab amplifier, I'm kind of wondering about how it would handle inductive or capacitive loads. For laboratory purposes, at least up to 20 or 30 kilohertz or whatever it'll go up to. It's, the minimum 20 hertz. I figure I can put my function generator waveforms into it, and it'll, I can amplify them up to about 70 volts if I want to, or, because I've got a really powerful receiver I'm not doing anything with. It's like 3 kilowatts or something like that, supposedly. It's going to be half that in practice, I guarantee you. You can't drive anything that high off of regular, 110 volt outlets. But at any rate, it just got me to thinking, what really is going on here? Because, and it got me realizing, it was never really covered in any of my textbooks. They just use resistive loads. Alright, and you might see down here, this is what a resistive load looks like. Okay, well, so I got to thinking, I'll bet you there's a circuit on Falstad I can go out and simulate. So, I found one of their generic circuits and modified it to run tests on it, and this is with an inductive load. Now, all my inductances, I'm only using 40 hertz and like the 1 kilohertz he talked about there. But, I got these all tuned to where they're basically 8 ohms of impedance at 40 hertz, because the theory should apply, which just happens to be the, at 8 ohms, that's the corner frequency of 40 hertz, as it turns out. They talk about it being at a 45-degree phase angle. So, which is, honestly, that's a hallmark, when you get a 45-degree phase angle, that's your corner frequency of a filter. But here's the same thing with a capacitor, again tuned to 8 ohms. And here is with a resistor, again, set at 8 ohms. So this is what you would normally see in a textbook, and this looks a lot like that waveform I showed you on that article. What I'm doing here, is, this is the power across the transistors. You can see the transistor light up, that upper transistor there. This is the power across the load in this case, which is 8 ohms, 8 ohm resistor. Alright, now I'm measuring the voltages and currents on both halves of the transistor, and you can see the transistor, the voltage across it is that blue waveform there, or that red waveform really, and that turns blue, and this is the voltage, across this lower transistor, which is the purple waveform. Okay, here, right here across this wire, I'm monitoring both the current and voltage across the wire, which is what those two waveforms are. So this yellow one is the current, and the green one is the voltage across at this point. So, what you can also see here, that's the voltage, as we run the simulation. You can see over here that, this thing, and again, this isn't going to be identical because he's talking about some hypothetical amp where you actually can drive the transistor fully to the power rails, but certainly in this amplifier you can't do that. But I assume it's a Class B amplifier because that's what they're very fond of on that website. But in any event, it can be really apply to any amplifier. But the point, one of the points he's trying to make is that, when you're driving inductive loads, the more inductive it is, the more of a burden it is on your transistor. And so, again, that's another little thing I wanted to explore, in addition to the fact that, okay, how the hell does a reactive component pull current from an off transistor. So, and again, I'm gonna try to do short little links and Falstad. I'll see if I can create a short link like this and put it in the description of the video. So you can pull this simulation up yourself and modify it all you want. But yeah, I did a resistor just to kind of do as a sanity check, and then I did a capacitive load and an inductive load, which is what he was primarily discussing. But you can see that the peak power here in this case is about 177 watts, which kind of correlates a lot with what he was talking about. That's the power in the transistor. But there's really no watt in the load, even though I'm not actually monitoring these, but you can actually monitor power on a reactive component. Apparently, let's see. View a new scope. No, I don't want to do that. Where'd that go? Falstad, I swear. Let's see if you can do it here real quick, but I tried it earlier and I couldn't, and it's not giving me the fucking properties. God, what a piece of shit. Anyway, let's see. Show peak value, but the problem is you can't show power. Well, no, you can. On my other computer, it'll allow you to do it, but it won't show you anything because there is no power consumed. So, even though there is temporary power or energy being stored and stuff, you can't really show that, but its net power is zero, always. But yeah, you can't do anything like that. No? Well, okay. That's interesting. It worked. It wasn't working this morning. Okay, so anyway, yeah, well, I stand corrected, so you can actually display the power on it. Falstad's a kind of a buggy little system, really. Okay, but so yeah, okay, guess what? You can, but you can see the power is above and below, the zero line, right? So that means, power is being gathered, energy is being stored, but then it's later being released and then going the other direction. So there's no net power like you see over here, because you should see all the power above the zero line, or all of it below the zero line, as the case might be if you got your stuff backwards. But the point is that that this is what a resistive load would look like. All the power is above the zero line, like it should be, in a resistive load, because in balance it's actually consuming power. If it was below that line, like this, inductance is, it would be equally above and equally below. That's a sign it's not actually dissipating any power. Of course, in reality, an inductor would have some resistance in there, would dissipate some power depending upon, what its winding resistance is. But let me go over here real quick, because that's nagging me now that I found out that you can do that. New undock scope, fiddle around, Falstad fighting me. Okay, go edit the properties. I didn't have to click it 17 times to get it to come up this time. Auto max scale, that's good. Show peak value. Like I said, I really, just want to show the average, power consumed, and then okay, and then let's speed it up. Alright, a little while. Okay. Alright, so basically this has got your capacitor right here. in power consumed. I bet you I can put the inductor in the same window, but I think that's what I was trying to do this morning maybe, and that's why it was not cooperating with me. So, um, so yeah, but yeah, you can show, what the apparent power dissipation is, and this is all apparent power because, you got a certain current and a certain voltage across this thing. Yeah, you'd think, hey, that's consuming a bunch of power. Well, no, it's not actually. It's just apparently consuming power, but in fact, it actually throws it back into the system, and that's what happens here. It's the device itself isn't consuming any power. Whereas the transistor here that's driving it is. In fact, you can see that's peaking at like 307 watts here, in this simulation, at peak power. So, it just kind of shows you, what goes on if you look at these waveforms. You can see that, look, this red waveform, alright, is the voltage across that meter that lit up, that 12.7 volts, where's that right now? But anyway, it peaks at 91 volts. Now that's a clue as to how this is working, okay? Because what that guy said, he said that, you get maximum current, which maximum current, is this yellow trace here, right? That's the maximum current, going through our wire right there. Alright, so it peaks at about 5 amps. And again, I tried tuning things to his figures as much as I could, with the frequency being different and the fact that you can't actually drive the output signal to the rail like he suggests. I had to use 51 volts instead of 40 like he talked about in his article. So that means there's going to be extra power dissipation here that, his ideal article wasn't really referring to, but it's still there. It's still a contributing factor big time in a practical amplifier. But at any rate, our peak current is 5 amps, but okay, what's the voltage across the transistor? Well, that's what I'm measuring with this meter here, and, so that's what that red trace is. It keeps flashing blue when I hover over it. Okay, so that's the current, but here's the voltage across it. Okay, now what's the voltage at peak current? It's about 50 volts, okay? So in some ways what he's saying is right, that is, at peak current, that is when the voltage across the transistor is about equal to the supply rail. But the thing is, that's not the peak voltage across the transistor. The peak voltage across the transistor, as you can see again by the red trace, is actually 91 volts. And that's because this transistor starts turning on when this is fully off, so that's where all the current is basically coming from. But, you can see, okay, so this is the dissipation of the transistor. It's peak current. Look at where it occurs. You can see this trace up here, but notice how this positions itself. Okay, so, we can go over here and say, well, where at peak power are we? Because that's what he's talking about. He's saying this is the peak power point. Okay, well, peak power, is actually occurring, again, remember the yellow trace and the damn red trace that keeps changing color on me. You can see that peak power is not only not occurring at peak current, but it's also not occurring at peak voltage. But, the voltage across that thing, where that's occurring, and again, notice this as I have my mouse down here, peak power is actually occurring when this thing, is about, like, what is it, 60, 68 volts or something, but it's certainly not, full voltage. It's close to what he was sort of saying, but, certainly even 51 volts is off a little bit, but it's certainly not peak current, because peak current occurs here, okay, that's, we're at 5 amps, but, the voltage drop across the system, is about 50 volts at that. So that's true, but that's not its actual peak power point. Its peak power point is a little bit over here. And again, some of this may be because I can't drive the signal to the full rail. I have a feeling that's why there's a little discrepancy between what he's saying. Because basically what he's saying is true. This is the point where you got 50, in his case 40 volts, but in my case 50 volts across the transistor. All right, and that does correlate with peak current occurring there. The thing is that that since I can't drive this transistor fully on, there's always at least an 11 or 12 volt drop across it, which you can see if I speed up the simulation. Just kind of pay attention to what's going on here. 12, 13, 14, it's up to 90 volts. Now it's falling, and it just never gets down to below about 11 volts. So it's always got 11 volts across it, even when the transistor is fully on. So any current that's going in there is, it's still dissipating power even under those conditions quite a bit. I think that's where some of the discrepancies coming from, because I still think basically this guy certainly knows what he's talking about. But at the end of the day, he doesn't mention some of the complexities of it. I think that's what's going on. But like I said, in a practical example like this, yeah, you got peak power that's actually not aligning, with what he's saying. Peak power in this case is not occurring, where the voltage of the, of the supply rail is being dropped across the transistor, so, it's certainly off a little bit. That, that point he referred to is actually not peak power, at least not on this. So, the peak power is occurring, like I said, about here. So, that's about the, 4 amp point, or it's close to peak. And again, because it's close to peak, I have a feeling the difference is because of that 11 volt drop, because I think he's assuming next to, a fractional volt drop, across it. But, in a practical amplifier, especially a Class B, that's kind of hard to do, I think. But at that point too, the voltage across our load, is here, all right, and but that correlates to the voltage across the transistor is, again at peak power, like I said, about 65 volts or so, 68 volts. So, so again, I think there's a little misalignment there. But again, I think his theory's basically right. But the one thing he doesn't talk about is the fact that, our peak voltage, is actually 91 volts. And that's not just, 50 volts plus, 10 volts or something. That is because this transistor at some point is operating too, and it pulls this voltage, it stretches it down, below ground. So, in effect, as this transistor is doing its thing, so, the voltage is actually, much, much higher, but that's not where peak power occurs, because basically the transistor is, kind of off at that point. The lower transistor is on, which this is a lower transistor curve right here, and that I'm measuring the actual transistor, where this right here is, this meter, and that's that meter, so you can kind of see how out of phase they are, 180 degrees out of phase. But this actually shows you that when, the closer this waveform gets to the ground line here, the zero reference, the more on the transistor is. So like this, the transistor we've been talking about, this peak value is actually when it's fully off. This trough value is, that's close to ground is when it's fully on. So it gets like 10.8 volts across it. But the same thing happens with this transistor. At the same time, it's fully off, but then over here, for example, it's fully on because it's as close to ground as it gets. So that's why I have this waveform on here in addition to these 2 meters. But, you can kind of discern what's basically sort of going on here. I mean, you got current flowing. You can see where peak power occurs, but it's not, it's not at full voltage drop across the transistor. It's just, at full voltage drop. Let's see what we got here. Because we're almost peak voltage here. But, peak voltage, that means the thing's, pretty much off, and you can see what's going on. The voltage here is very low at 13, and we got 3.3 milliamps going through it, but we got 1.7 amps going through our top transistor still. So, so the transistor, is hypothetically off, but it's still conducting a lot of current through it. Yeah, anyway, I did, open up this new window. I just want to take a break and look at it. But here, like I said, you can see that, we're almost, at the peak of the power waveform, peak power dissipation in the transistor. Now, since this is a capacitor, remember, current leads voltage on a capacitor. So even though the transistor is actually, you can see it's off here, and it's actually just starting to turn on. But you look at the current's already at, near maximum, even though it's not even, it's only just in the process of turn on. That's why it has 72 volts across it. So that's why we're getting, huge peak currents, because it's got 72 volts across the transistor, but, the voltage across our capacitor is still minus 21 volts. So basically it's in the process of bringing that capacitor from a very low voltage, up to ground level, and then ultimately it'll charge it positively. But by the time it's doing that, the current's falling way off. So once the voltage is at peak, which you see here, what the voltage versus current waveform is. When peak voltage actually corresponds to zero current on a capacitor. Alright, so in other words, the peak voltage, alright, it occurs when you got peak voltage across the transistor, in this case. But it's the lower transistor, that you're getting the peak voltage across, because again, this transistor is well, it's 100% turned on at this point, okay, so that's what you would expect. So that's when you get the peak, voltage across the capacitor is when the transistor, is fully on. And the purple one is the lower transistor, and the red one is the upper transistor. The upper transistor is fully on. That means the transistor has minimal voltage drop across it at that point, and that means the capacitor, with reference to ground, has charged up to as close to the power rails it's going to get. Alright, that's when, minimal current occurs, but that's also when the transistor is fully on. Alright, but, like you see right now, we're just reaching peak power here. Well, our current, is 4.2 amps, but while our voltage is still 72 volts across the thing, because the capacitor hadn't, still got a negative voltage across it, basically. So, as you can see here, and I know this gets a little confusing, but these two are not connected, and, you got to learn to kind of ignore that. They look like they're connected, but they're not. But, yeah, right now our voltage across the capacitor is still negative from when this transistor was on, and it had, pulled it down to a negative level. Well, now the opposite is true, but this transistor first has to charge this thing up to ground before it can start charging it above ground. But again, that's when maximum current's going to occur, when this voltage across this capacitor is highly negative. Alright, so, because it's, uncharged capacitors, for example, act like a short circuit. And that's the way of keeping in mind why current leads voltage on a capacitor, because you got to have a really high current. A short-circuited capacitor, draws maximum current with no charge stored on it. As an example, it's an easy to remember example. That a discharged capacitor, when you first start applying voltage to it, will draw maximum current, especially if you're applying a sine wave. But by the time the capacitor is fully charged, it's drawing zero current, because it's stored all that charge in there, and once the voltage of the capacitor equals the voltage of your power supply, well, guess what? It doesn't need any more current. So that's why voltage lags current. Our current leads voltage in a capacitor. It's just the opposite of an inductor. But at any rate, this kind of gives you a clue, if you want to try to understand, impedance loading. And this also shows you why. I mean, look at that, 307 peak watts in that versus our resistor version, which was 80 peak watts. But it's broader, but it's still way less overall dissipation, but you got actual full dissipation in your load, so that's about the best you can get. These two powers are probably approximately equal, via the maximum power transfer theorem, I assume. But the point is that actually they may not be quite equal, but the point is that here this is actually dissipating power on the load, so there's less power for the transistor to dissipate. But basically over here, in the circuit we're just looking at, well, there's no power dissipated in the device. It's got some power here, some energy stored, and then it releases it and throws it back into the system later. So guess what's catching that? The transistor. It has to absorb that power because there's no load absorbing it. So that's why having an inductive or capacitive load, you often see warnings like on lamp dimmer, not design, lamp dimmers, for your wall, to control your room lighting, not designed for inductive loads, meaning don't try to drive ceiling fans with them. That's why, because it could cause, because the inductance of the motor, it can cause, the triac in there to overheat, because it's having to eat all that freaking power that that is coming from that stray inductance, in the motor. It's having to eat all that, and that can exceed its, limits quite easily. And that's basically what this guy was talking about in his little article, is that, it's a good article, and this shows the different phase angles, caused by different power factors. And if you have a power factor of 0, which is 90 degrees, which is what we're dealing with, the peak power is, about 4 times what it would be under normal circumstances. So again, what he basically is saying here is that if you had a pure resistive load, on your amplifier, well, it may be that, hey, a 50 watt transistor will do it. But in fact, because of the power factor problem here with a pure inductive load, you would need like a 200 watt transistor, or better. And, but in practice, a lot of these times, like with speakers, he's saying it'd be somewhere in between that. But, because you're never going to have a purely inductive load speaker, but you might if you're using it as a piece of test equipment, which is my interest. I'm not really that interested in stereos or anything. I'm really more interested in just general technology and test instruments, that kind of thing. So, but I've always been curious about inductive loads on amplifiers, and how that actually affects them, and why it's so bad to have an inductive load on it. I've just never seen it even remotely quantified before, and this is the closest I've ever seen is this article. It's a pretty good article, and you couple that with a little tool to play with, like I have here, you can learn a few things with it. So, and again, I know this is kind of confusing, and especially with all these things. It's Falstad. I mean, it's the best I can do. But it's a free simulator, and it's easy to provide links to circuits you do. I even made a separate video about saving files and some of the other quirks about Falstad, like, yeah, I guess I can go ahead and do that. Let me speed this thing up and hit reset on it. No, it's not doing it. Huh, that's weird. Anyway, my other video, I actually show you if you have a brand new simulation. I don't know why the hell it's not resetting. Maybe, it's not doing it anymore. That's weird. But at any rate, that if you, maybe it's because in the other simulation I was using the inductor, which, like I said, I haven't talked much about the inductor version of it, but you can see that, before I reset it, you know, that this is the waveform for an inductor, and this is the waveform for the capacitor. So you can see they're like opposites of each other. They're kind of reversed. But you know, there really shouldn't be much of a difference between an inductive load and a capacitive load when it comes to amplifiers. You know, because I was like, well, they both store energy and throw it back into the transistor. So, you know, you only see warnings about inductive loads, you know. But no, I mean, capacitive loads of similar magnitude would be equally problematic. You know, it's just like in a lamp dimmer, you only see that because they don't expect you to have a big capacitor hooked to the damn, you know, the light socket up there. But you might have a ceiling fan, so that's where that comes from. That's why there's sometimes they talk about one, not the other. But really, it's reactive loads, you know, in general, that are a problem with overheating transistors. And just like they talk about this article, you know, it has a lot to do with the safe operating area. And they say that average power is not what kills a bipolar transistor. You know, it's peak power that does it, because it actually generates a little hot spot. You know, a large power transistor, like, for example, if this was the die, you know, this square rectangle here were the die of a power transistor, well, because of that peak power, it may develop a little hot spot like right here, okay? And, well, if it does, since that hot spot, you know, it changes the beta of the transistor in that little hot spot, you know, which causes thermal runaway to occur in that little hot spot, you know, which will basically end up blowing a hole in your die, or, you know, giving it a meltdown, basically. And that all happens very quickly, just like you discussed, you know, within milliseconds. You know, it can destroy your power transistor, you know, because of that peak power, you know, nailing, you know, that secondary breakdown, they call it. And, you know, they got another article, too, down here, which I'm in the process of reading, on secondary breakdown, which I've been familiar with that for a while. But this actually elaborates a lot on it, you know, and but there is an article, a link. Let's see, it's an amplifier design article. They do have an article here at the end. That, you know, SOA. Yeah, remember to see the SOA article for more detail. So again, you know, you can click on that too, and that'll go into more detail on it. Although I've glanced through it so far, and I still think they've left some things out that, you know, actually show up on modern data sheets. But I haven't read it yet. So, but basically, you know, with a power transistor, the higher voltage across it, you've got to really way to rate the transistor way below what you would think its power rating should be. You know, so you may think, oh, this amplifier, you know, this transistor should be good. You know, if I run it at, you know, 50 volts, I should still be able to get an amp out of it based on, you know, the calculations and everything that's suggested. But no, because of the safe operating area, you might be lucky to get, you know, 100 milliamps out of it, you know, at 50 volts. You know, that's why most bipolar transistors, you know, the only way you can actually get any real current through them is under 30 volts. You know, so just make sure they never have 30 volts across them with 1 amp of current. But this, you know, article, you know, basically shows you that, yeah, there's some caveats to that too, you know, because of when peak current may occur versus, you know, your peak power, you know. So it's not necessarily simple if you got a reactive load. You know, if it's just got some minor reactance in it, you know, it can often be kind of trivial. Like he was talking about in this article, but you know, in that table there, for example, let's see, yeah, you know, but it can often be trivial. Like if you had a 15-degree phase angle, it's about 1.38. So, you know, as far as the peak power versus 1, you know, because it's been normalized to this wattage, so. You know, this is 100%, this is 138%, this is 200%, this is 400%. So, you know, so in other words, you need a 1, 1.3, 2, or 4 times more powerful transistor if you want to handle these different phase angles. So, anyway, you know, the higher the phase angle, the more powerful the transistor, the more money it costs, and the bigger of a heatsink headache you're going to end up with. At any rate, you know, that just I just wanted to kind of cover that issue because that was pretty it's just something I've wondered about for a long time. I've just never seen the material that deals with it. I mean, shit, I don't even know in a college course what courses would take that. It's certainly not basic semiconductors, I'll tell you that, unless it's like some homework problem the instructor gave you. Um, Other than that, I mean, they hardly cover, in the books I've read, they hardly cover, reactive loading of any kind in any semiconductor situation. You know, um, this guy also talks about FETs, and that's another thing you're going to find interesting here is that there's a different. It solves another little issue, because supposedly, MOSFETs didn't have thermal runaway problems. You hear that all over the internet, but then you hear, well, the new ones do, and he actually talks about that in the same article, down in here. That there's certain kinds of FETs, but they don't really make that much anymore, so they're hard to get. But they're from the days when they used to use MOSFETs as amplifiers in stereo equipment, which they do so less today apparently. But those were like lateral FETs or something that I'd have to find it in the article here. But those types of MOSFETs actually are more or less resistant to thermal runaway, just like you hear about all over the internet. But these vertical FETs that are designed for fast switching apparently aren't as good at handling that. So, so anyway, there's a lot of good material on this, on this Elliot Sound Products website. It's got I've been like, I've noticed this for a while. I've just never realized how good some of the material actually is here, even though it is lacking in some ways. It's not, like heavily math oriented or anything, but it's meant for amateurs, So, people trying to do their own stereo amplifiers, and and there's lots of electronics projects on here and stuff. And it goes a bit outside of just stereo related stuff, but it's primarily focused on that. I mean, very primarily. But anyway, it's worth a check, and a look-see, dig around on it. You'll find some interesting stuff here. So, I think that about covers it. So, cheers.